The team of Petroleum Engineers Association is delighted to organize this webinar session on the theme Well Control Incident Basics and Lessons Learned. We are very pleased to introduce Dr. Nitish Kumar, owner of MDNK Oil and Gas Consultant, former professor and HOD Petroleum Engineering, DIT University. Dr. Kumar runs a well engineering consulting company called MD&K Oil and Gas Consultant, which for the past 2 years supported ONGC KG-98 by 2 project offshore KG basins. Earlier, he has served the department as professor and HOD, and prior to that, Dr. Kumar held the position of subject matter expert for well engineering at Petronas Kareli, headquartered in KL, Malaysia. He was focal person for well engineering ROV intervention, plug and abandon and barrier integrity for worldwide engineering planning and employment execution at PCSB. He has 18 plus years hand-on experience in the field of well engineering and drilling technology. Dr. Kumar started his career with Murphy E&M USA in the New Orleans as an associate drilling engineer, where he put together drilling program for well drilling Medusa and frontier fields in the Gulf of Mexico. Then after he worked in various parts of the world, NCS, North Sea, offshore Tanzania, Spain, and India, Sahara Desert, and Malaysia in various consultancy, engineering, and managerial roles with companies like BP America, Statoil, and Shell. At this time, I would like to tell that there will be a Q&A session at the end of this webinar where you can ask your question related to the topic. Now, I would like Dr. Nitish Kumar sir to start this webinar session. Thank you, sir. You can start.
Thank you, Nikhil. Am I audible to everybody?
Yes, sir. You're audible, sir.
Very good. So first of all, let me thank Petroleum Engineers Association for inviting me to speak on well-controlled incidents um, and some basics. Of course, many of you are college students, which usually makes my majority audience. But as a student, you will learn about basic best well-controlled uh, well-controlled concepts in the classroom, and also maybe if you're preparing for IWCF. However, you kind of miss the essence of it when it comes to application. So this is a very unique topic, guys. On one hand, we will cover some basic concepts, and the second thing would be about the lessons learned, how to manage incident control, and what really happens in case of a well-controlled incident on the rig side, where people make mistakes. So that is the theme for this presentation. Hope you will enjoy it. All right. So let me take you to the next slide. So before we start with the basics concept, over here we will talk about some basic concepts, of course, then we will talk about basic well-control concepts, then we will get into examples from industry, and finally, what are the lessons learned? We'll talk about that, okay? So what is well-control? It means we are talking about methods which are used to minimize the potential of the well to flow. What does that mean? Flow from the reservoir to the surface in an uncontrolled way. That is very important, guys. Uncontrolled manner. If the flow is uncontrolled, if you cannot have any control over the well to flow, then there is a problem. This will eventually end in a kick, and then you all are aware of incidents like Macondo and so many well-controlled incidents around the world, basically you have to breach a wall barrier before it can really be a big catastrophe. We'll talk about basic concepts in terms of what a well barrier is, how drilling mud becomes a family barrier, and we will also look at a little bit on the drilling methods which we use for well control and what are the causes. We'll look into the signs which lead to a well controlled situation. And it is important that it's not just for drilling. A well control incident can happen in a well completion phase, a well workover, abandonment, or well servicing operations. So it can be either way, not just for drilling, but any of the operations we have in the oil industry. So keep this in mind. But this presentation would basically focus on drilling. All right, guys. So let us start with the presentation with porosity and permeability. When we talk about flow in the formation, basically we're talking about two things. One is your porosity, which is the pore space, uh, empty space in the rock matrix. Yeah, and that is empty over the total space in terms of volume, and a good porosity, like a good sandstone in Gulf of Mexico or Beria sandstone, might have a Darcy in porosity. Darcy is its measuring. You talk about poor porosity, and sorry, porosity is purely by percentage. But when you talk about permeability, the unit is Darcy, and flow is in the pore spaces which are connected. Yeah, connected means where they have the ability to flow from one pore to another pore, and that is what is measured in Darcy's or millidarcies. Now in Gulf of Mexico, like I said, one Darcy is kind of not a big surprise if you have that kind of sandstone. But you come here to the KG Basin, offshore India, and you're talking about a couple of millidarcies. So which one will flow more? Whether a Darcy or a millidarcy, obviously it's the millidarcy which will not flow, and so it's not a good reservoir, it's not a good reservoir rock. So when we talk about well control, we must understand that having a good porosity and good permeability really makes a good reservoir. Not only that, it will have the ability for fluid flow from reservoir into the well better than a rock which has poor permeability and porosity. Overburden effect. Yeah. So what is overburden? It is simply the pressure exerted on the formation at a given depth due to the total weight of rock and fluids above that depth. Yeah. Now you can have a very high overburden stresses as well, because as you go deeper, the total weight of the rock above that particular depth would be much more than at shallow depths. So if you're talking about wells in Gulf of Mexico, where the depth can be as high as 25,000 feet, 30,000 feet, 33,000, 35,000 feet wells are there, you will have a much higher overburden stress. But if you go to, say, Malaysia, where you have maybe a shallower, comparatively shallow wells, or in North Sea, Norwegian continental shelf, 10,000, 15,000 feet wells, the overburden stress won't be as high. So you measure the density of the formation in terms of specific gravity, and and also you can talk about in terms of PPGE. That is, usually we talk about pore pressure in terms of PPG. Now that equivalent overburden stress, overburden effect, you can, for the rock also, you can do almost like 19 to 21 PPG. So moving forward, let's talk about pore pressure. Is the pressure of the naturally occurring fluids within the earth. So what cools a rock to have all that pore pressure? It's the, of course, there is a rock. The rock is, if it's a reservoir rock, there would always be some kind of containment to that rock. But it is the overburden load on the reservoir which really holds that, that fluid inside the rock. So that said, you can have three different kinds of pressures for the rock fluid. One is the normal formation pressure, which is simply the water present in marine or seawater environment and to that depth. So if you're talking about seawater rate of say 8.3, 8.33 ppg, and or to a depth of 10,000 feet into 0.052, 8.32 into 0.052 into 10,000, whatever it is, that's the normal flow pressure. That is normal. Then there is a category of subnormal formation pressure, which is pressure that is less than the corresponding pore fluid hydrostatic pressure. Why would you have subnormal pressure? There are many situations, and there are reservoirs worldwide where you can have a subnormal formation pressure, 6 ppg, 5 ppg, that kind of reservoir pressure have been seen. Say in a depleted reservoir, what would happen if you have been producing in a reservoir for several years? It would be a depleted reservoir, it would be just subnormal pressure. Likewise, you have abnormal pressure or higher than normal pressure, and this is the this is when you will say that the pressure of fluids in the rock is much more than the normal formation pressure. So if it is at that depth, an equivalent weight or pore pressure is say 10 ppg. I mean, if it is not 8.33 or 8.7 ppg and it is 10 ppg, yeah. And where does that happen? It usually happens when you have different situations in the reservoirs at different pressure. We will see all these cases as we move forward, and I will discuss. So, looking at the abnormal pore pressure, here you can see that you have the ocean or the riverbed, and then there is a cap rock. Cap rock is nothing but the containment, the seal. And this seal, if you look at, you have basically below this, you will have the reservoir rocks. And what can be the seal? Maybe shale. And you drill through it and you see overpressure. Why? Because this reservoir fluid is under pressure, significant pressure due to the gas or say below ramps and cap rocks is the first thing. Yeah. Why? Due to reservoir fluid in the rock. You have salt beds, you have salt domes, right? Uh, you have uplift and erosion that can cause abnormal pressure. You have artesian flow. What does artesian flow mean? You are at a higher altitude, water is flowing at a higher altitude from out, and then you're drilling at a lower depth. Say you're in the Himalayas, and uh, there is an artesian which is flowing from higher up, and then uh, it is connected to your reservoir down, then whatever is the weight of that fluid from all the hydrostatic from that depth, that will be added. So in Pakistan, you will see that there are wells where you have to use 18, 19, 20 ppg muds, just because there you have the issue of drilling in, in a mountainous rocky region where there are reservoir rocks which are connected way up with artesian water bodies up in the mountains. Likewise, what happens in salt? As you all know, salt is a um, semi-solid state, kind of lava or liquid. Some tectonic forces are acting because of which all this uh, liquid rock is there, and when it moves up with a lot of pressure. So all this can cause a significant amount of pressure, and if you are drilling through and you hit in there, the salt, you may get into a situation when your bit can get locked in that salt, and then you won't be able to pull it out. So that kind of abnormal pressure has been seen in Gulf of Mexico, say in People Canyon area, when you drill through that salt and then the whole well was lost. So they have to cut the PHA, pull out, and sidetrack. And again the same. There was the Chevron well in People Canyon 819 they were drilling, and that was such a mess that the well took almost 2.5 years or 2 years to drill. So, there are many such examples. All right. Next is levels of well control. So, what happens if there is a flow of reservoir fluid to the surface, like we said? Yeah. So, and how many levels of well control would we have? So, the first thing is the primary control is the mud itself, the drilling mud. As long as you have the drilling mud in the right way, in the right properties, you have the best well controlled uh, fluid the means for the well. That's what we call prevention. And once this prevention is lost, they go under, uh, you go underway, and the reservoir pressure is more, the formation pressure is more than the hydrostatic plus the uh, frictional pressure due in the well, then what will happen? You will go under balance, and in that case, you may need a secondary well control. And what it is but something like DOP ramps, yeah, or the annular, you shut on them, and then you circulate out that tick, and you try to maintain your primary mud rate just by, if you're using driller's method, maybe two circulations, rate and rate, on-current method, whatever method you use, you try to bring that overbalance back and get into the primary control zone. But if even this secondary control fails, and then you get into tertiary control, which is like you would like to bring in boots and fruits specialists like them, and like in condo, so many vendors were involved in controlling this big well control problem, and that becomes a mess. So you can see primary well control is prevention, secondary is control and recovery, whereas if you go into tertiary control, it's really mitigating the problem. So you need specialists for that. Now I just bring in a slide on well integrity and well barriers. Why I bring in is this subject, this topic of well integrity is a very detailed topic, and those in the field do realize that when they put together drilling programs, we try to maintain at least two barriers, two well barriers in place, and the well barrier is made of various barrier elements. Now you can see in this schematic there's a reservoir, and we are having a directional sort of road here. So there is reservoir here, and to some extent, of course, this casing is a barrier, but then as it comes out of the reservoir in the hole, this casing, this blue thing is your primary barrier. And as you go further up, you see another barrier. This is the red one, the cement behind in the hole, and that's the secondary barrier. Further up, as you go, you have this cement all around, and you have your VOP, you have well-controlled equipment as your barrier element, and together all this is your secondary barrier. So you see there are two barriers here, and that's what is recommended. Most companies recommend for two barrier element, and when it comes to well control, that incident will not happen unless and until one of the barrier elements is broken, and then both the barriers are gone. So it's not just one, but two barriers are gone. Now, why I said initially one was there are special situations when you would allow the same barrier element to act as the primary as well as secondary barrier element. This is more in the completion phase, or there are whole different uh, detailed analysis and study in this area of integrity. Here we'll just touch from point perspective of drilling, and we're talking about drilling mud basically. So my next slide is about barrier element acceptance criteria. Now, fluid column. Fluid column, as you know, is barrier, basic barrier element. And you see, this is coming from North Code D10. And when we talk about drilling fluid and drilling mud, you see design and construction selection. So in the design phase itself, you must ensure that your well design is such that the hydrostatic pressure shall at all times be equal to the estimated or measured pore reservoir pressure. That's exactly what we plan as drilling engineers. We try to have a safety factor there, but as engineers, we can only plan, guys. When we go in the field, and then that hydrostatic pressure, and when we drill with a specific hydrostatic pressure on, and we need a big ramp, which we had not been able to predict geologically, because what would happen? We'll end up in a well controlled situation because we are going to take a kick. So once you have taken a kick, then of course that is the purpose of the discussion for this particular presentation. But that said, it is important from well barrier element acceptance uh, criteria level also that you should plan the wells in such a way that the pressure, the hydrostatic pressures are in the proper way. So that's why it's simpler, easier to design a well where you have existing fields or where you have drilled some wells than in a wildcat area. So the second point is critical fluid properties and specifications shall be described prior to any operation. So what critical properties? The YTD, the PV, all kinds of geological properties should be well described, and your mud engineer takes care of that. But that's also an important criteria for barrier element. Then the density shall be stable with specified tolerances. Yeah. So it shouldn't be that you were at the surface temperature when you went in the hole, and then when you try to reach your HPH reservoir, this mud will not work at a higher temperature and pressure, then you need to change your drilling mud. So all that design is done in the proper way and at the well-planned stage. Hydrostatic pressure should not exceed the formation factor pressure. So this is a very important point. Hydrostatic pressure should not exceed the formation factor. So, and there should be a safety margin. This is very important, yeah? And then changes in valve pressure caused by tripping. So, surge and swap. We will discuss this in the next slide. Yeah, in drilling operation, drilling is important, of course, but tripping is equally important. Fluid circulation is important, and we should estimate and include the safety margins in our design. So, you see, and then there are verifications and initial tests, testing, blah blah. You monitor them, now monitor the well barrier element. Now, this I'm talking just for drilling fluid. There may be more than there are 104 or 110 barrier elements in North South 310. And if you were to go through all those elements, you will see they have deliberated on design consideration on each element. Very useful document, and I would recommend that if you want to get into the area of well control, well integrity is important, and you should have a look at this North South 310 document. Moving forward, guys, so we talked about swab pressures. So what is swab? It's a piston effect when you're tripping, you're trying to pull your bit out of the hole. Yeah. Then this causes a decrease in the valve pressure. And if that decrease is significant, what can happen? You may end up in a situation when the reservoir fluid will start flowing. Now, if the reservoir fluid influx happens, you have taken a cake, and that's something which we don't want to happen in drilling operations. But you will see that in theory, to discuss about swab pressure or surge pressure, I'll just discuss that as well. But this is very important. From swab and surge pressure perspective, I would say that the operators on the rig side must be aware of the impact. We'll see in one of the wells cases how careless we can be in situations, right? So, talking about surge pressure is the piston effect of downward spring movement. Yeah, when you're going down, and this piston effect happens on the valve bore, and if you don't have control on the surge pressure, you can end up in fracturing the formation. At one end, you can take an influx, and on the other hand, it can be fracturing the formation. So if you fracture the formation, guys, what's going to happen? Yeah, your mud level will go down. When the mud level goes down, the next thing you will know is you have taken an influx. Why? Because the hydrostatic is not enough to counter the formation pressure, right? So both swab and surge can lead to a kick if we are not careful enough. Trip margin is the hydrostatic overbalance required to safely compensate for swab pressure. Pump surge it's just breaking the gel strength of the mud and accelerating the mud column, and that will require to increase the pump pressure. So if you increase the circulation slowly, then it's you have better control on the pressure. Otherwise, you can break something down with the pumps. I will give you an example of this. So what's happening here, guys? Just have a quick look. So your formation pressure is at 5400 psi and pore pressure 4500 psi. So your bottom hole pressure should really be between 5400 and 4500, right? Now, what's happening? There are two cases here. Let's talk about swab and Let's talk about surge. So swab, you start pulling the bit, and when you're pulling, it just runs very close to the formation pressure. What can happen? You can take an influx, right? But on the other hand, you are trying to pull, you're trying to go in the hole with a lot of force, a lot of pressure. What will happen? The, the well will surge, and then you're getting close to the formation fracture pressure. In both the cases, you have one. Now, you see, in the swab case, yeah, in the swab case, when you were trying to pull the formation pressure, you're trying to pull the pipe out of the hole, what would happen if you switch off the pumps? The additional pressure from the pumps is also gone there. So you will lose pressure there as well, right? And in case of surge, you see, a surge can really be a problem because here, if you have the pumps on, what will happen? Pumps on plus surging going down, and if it is reaching the formation fracture pressure, you start losing. You'll start losing mud and the drilling fluid. Now look, what should be your goal? Your goal it should be to be in the yellow ring and below the formation fracture pressure. So your bottom pole pressure is key, guys. Okay. So what is a kick? It's an unwanted or uncontrolled flow of formation fluid into the valve. Yeah, uncontrolled flow refers to flow when bad is that right? When will the formation, if in a condo, if the cement was in place behind the casing, do you think the reservoir fluid would be able to come all the way to the surface? No. Okay, if the seals were in place, even though the cement was not there, will the reservoir fluid be able to get inside the well? No. Well, if the operator was able to close the BOP and the intermediate casing seals were in place, either of them were working, would that cause this well control incident? No. That means there are so many checks and guidance available to hold this kick to come from reservoir all the way to the surface. And we could have stopped that well-controlled incident. But due to multiple failures, this incident happened. So let's get to the starting point. Okay. Unwanted or uncontrolled flow of formation. Okay, let's see. What are the causes of kick? Why do kick happen? Main causes: failing to fill the hole properly when tripping in or out. Fill the hole properly. What does that mean? The volume of the mud which is being displaced when the pipe is being removed. That needs to be considered. Considered for what? The equivalent amount of mud must be replaced in the hole. Next, swabbing in a kick while tripping out. So you're tripping out, just we talked about the swabbing. Insufficient mud weight. Of course, if you don't have enough mud weight, you will take a hit. Abnormal formation pressure. You're drilling through a ramp, you come across this ramp, and you don't have enough hydrostatic pressure. What would happen? You will end up having a kick. Lost circulation, guys. Lost circulation is a situation that really happens due to mostly when either the reservoir formation, the rock is weak, or due to man-made situations, man-made created situations when the hole is not full. Then what will happen? There would be a when the loss circulation happens, the mud level will go down, and you will have a situation when you take it. Shallow gas sands. When you have shallow gas, yeah, when there is shallow gas, there have been several cases that this gas, when you're drilling through the sands, there is a kick. Why? You don't really have, when you're drilling through shallow gas, you don't really have a POP on. You have a diverter, basically. And all this gas, even though it may be for a short period of time, it comes up and it's diverting on back in the ocean or land where it is. So these are charged sands which have all this shallow gas, and they must get rid of the shallow gas. Excessive drilling rate in gas-bearing sands. So you get all this drilling rate. There are D components. There are all kinds of equations based on your resistivity logs and whatnot, and they will give you a drilling rate, and there can be a drilling rate associated with it, which can be identified. These can be the causes of the kick. How many kinds of kick indicators do you have? You have positive indicators when the kick is in progress, when you're drilling, or uh, you have signs of approaching balance, underbalance. So let's discuss quickly these during drilling and during tripping indications that a kick would show. Note that when the flow rate increases, that's a definite indication of a kick. When pit volume increases, that's a definite indication of a kick. Pump pressure decreases. Pump pressure decreases. Pump stroke increases. Note this. Pump pressure decreases, not increases. Pump pressure decreases and pump stroke increases, you will have a kick. So these are definite situations. You can face this. There are several IWCF questions based on very basic understanding of indications of a kick. When the pump pressure decreases and stroke increases, you have a definite kick. While you are tripping, incorrect hole fill volume. Why would that happen? You will have an incorrect hole fill volume if there is influx. Yeah, if there is influx, what would happen? The well will start flowing. Hole keeps flowing between stands. So you're trying to make up connections and the hole is flowing. So what does that indicate? It is a definite sign of a kick in progress. And this is when you're running in. Presence of some of the presence of some or all of these indications require the flow check to be carried out. So guys, what is our solution? If we have kick or if we have a positive indication of a kick, what is the solution? What should be the first thing an drilling supervisor should do or a driller should do? You should stop drilling and you should go for a flow check. But I'll give you examples and you will see they didn't do a flow check or they did a flow check when it was not required. Yeah, so we'll talk about those. So talking about indications of approaching balance. When you say approaching balance, guys, or rising formation pressure, that means the kick has not really taken place as yet. The kick is not in progress, but a kick can happen if you do not take preventive measures. Drilling rate. Yeah. If there is a drilling rate, that means the formation is changing. Like we said earlier, a drilling rate is very useful to identify change in formation and is usually associated with change in gas, background gas, total gas. Torque and drag, still on connections. Well, what does it mean? What would happen if you go under balance? You will take a kick when you go under balance, right? So, what would happen if you go under balance? And if there is a shale formation around you, then because of because the shale has that property of taking the water content on the mud, it will start swelling and it will behave erratically. It doesn't have enough overpressure to counter it, and then you will see that the torque and drag will increase. So, if you get an increase in torque and drag, know for sure that this is an indication of approaching balance or the rising formation pressure. Total gas levels. So, guys, like I said, gas level, what does that mean? If you are having increased gas levels, whether it's background gas, connection gas, they are indicating something, right? Where is this gas coming from? Maybe from the formation, right? Where else can it come from? Formation. So, and you may even have a situation when the gas is mixed up in the mud. Say in synthetic muds, you won't even know if the gas has mixed in the mud because they are so gas friendly that you won't know. And, uh, and then it comes to the surface all of a sudden, it kind of explodes. Flow line temperature. Yeah, change in temperature at the flow line. What does that increase? It means the formation is changing, temperature is changing as you go deeper, and a significant change means something is going down which you should be capable of identifying. Mud flow property, yeah, change in mud flow property. You were sending in a particular YP for the mud, a mud with certain rheological properties, and what you're getting in return from the whole is a totally different mud rheology. Why does it change? If you talk about salinity, yeah, mud salinity, and you are able to measure it very frequently, what would that mean? That means that there is some kind of influence somewhere. Shale density, cuttings, cutting sizes, yeah, sharp cuttings versus what kind of density of shale you get in. All these just defined as indications, rising formation. All right, guys. So you know what kill is. You know now that you have taken a cake, what is your option? Your option is you have to kill the well, right? How are you gonna kill the well? Uh, Basically, most methods try to put the constant bottom hole pressure, and here we will discuss Lewis method, weight and weight method. There are many other methods, not many, but two, three more methods. Circulation is one. You can strip down if you need to. But over here, we are just talking very basic one, Miller's method and weight method. The principle, if you think of the well as a U-tube, is formation pressure that you want to keep constant is the sum of hydrostatic pressure of mud in the drill pipe. Important that the pressure is measured on the drill pipe side. Why? Because the drill pipe side fluid will not be contaminated, right? Plus the shut-in drill pipe pressure. That makes your formation pressure. On the casing side of the U-tube, what do you have? you have hydrostatic pressure of mud in the annulus, yeah, which would be of lower density than what you had in the drill pipe, plus the hydrostatic pressure of influx, whatever influx you have taken, plus the shut-in casing pressure. So you can come up with the formula for kill mud weight based on these two concepts, and we can skip that for now. I will just go and talk about driller's method and weight and weight method. So the best part of driller's method is circulation begins immediately. Yeah. The first thing is let the influx be circulated out of the well with original fluid weight. In the initial circulation pressure, that must be held constant during the first circulation. Then, for underbalanced kicks, a second circulation is required. Why? You will need to know the kill mud weight and then circulate it around the well so that you can get the original well control, the primary well control with the drilling mud. And if there is a mechanically induced kick, then you don't really need a second circulation using a driller's method. So what is the good thing about driller's method? Immediate circulation, and the barite supply is not required to begin procedure. You don't have to wait for anything. You just go and start your circulation. Disadvantage: what would happen when you circulate with an underbalanced mud for a long time? There is influx pressure, yeah, and there would be a second round of circulation with the kill weight fluid, and that means the well will be under pressure for a longer time on choke. That's a disadvantage, right? Likewise, higher surface pressure than with weight and weight when the kick really comes out, and then the shoe pressure that will also be high. So, so here are the basic steps. We'll quickly go through it. Shut-in drill pipe pressure, as you see, the kick is in the bottom. There's a gas kick here, and you have some shut-in casing pressure. So basic shut-in problems in IWCF are based on this schematic, guys. And what you see here is uh, this is just before start of circulation in figure A. Now that was here in figure B. You start the circulation and with the original mud in the hole, and the gas starts moving and expanding as it moves up, increasing the pressure, casing pressure goes up, and that's circulating out. And first circulation is complete when the kick is all out, and then you close in the well, and with the original mud weight in there, now you must start the second circulation, and here you pump in the kill mud weight. And what you see the drill pipe pressure starts going down. It goes down, down to a final circulating pressure as and when the drill pipe side is full with the kill mud. And then you go further with the kill mud with maintaining the FCP on the drill pipe side, and you will see that kill mud is coming up in the annulus, um, and you maintain your FCP side and casing pressure. Uh, you're observing that as it goes up, and finally you see that the kill mud has been circulated all the way in the well, uh, and basically if there is no kick in the hole, there is no influx, Tail mud is sufficient to take care of formation pressure, so 0 psi on both casing side and hillside side. All right. Next, let's talk about weight and weight method. This is sometimes called the ingenious method, and what it is, guys, is you will have to wait a little bit. Um, Weight is increased or weight up prior to circulating, so that takes time. And this is required for killing a kick that requires a heavy fluid, not fluid weight. Generally, the well can be killed in one complete circulation, so that's the advantage versus a Phillips method. And additional circulation will be required to increase fluid weight by suitable safety factors. Yeah. So there are a couple of advantages: lower pressures on the well. Uh, Difference is most significant if the flux is fast, and they have done good calculations on this for large volume cakes. And then you have maximum pressure exerted on the shoe will normally will be lower in breaking rate versus Miller's method. Uh, and then, the well will be under pressure for a less. All this is basic concepts, guys. No big concept you are, I'm sure you're aware of drillers and weight and weight method. Now here, let's talk about well control incidents. So the kick has moved up and you find and they have a blowout. Did you plan for it? No, I didn't plan for it. As an engineer, I was really planning to drill a safe well, just the contrary. But shit happens, guys, and this is one thing which happens in the oil field. Blowouts happen. There are environmental impact of blowouts. Yeah, you will see a big fire in the middle of the ocean, gas is seeping out, and or maybe bubbles coming out around the rig, and then there's a big spark around there. Uh, there is there can be situations in Algeria. I was on a rig where a lot of semen came out, all dry semen, yeah. And then you can have a multi-well platform and a big blowout, and then the whole platform is gone ashes. And there have been cases when the pressure has been so significant that the drill pipe really flows up all the way up in the air, yeah, and hits the derrick and whatnot, and everything is damaged. You go to North Sea, and you will say, uh, you know, there have been several cases there also. It used to happen. A big one happened in 1976. There are many other happening, but there are smaller incidents now than there used to be in the initial days. But we need to keep improving that. Breach to surface in an offshore environment. There are side tracks when you're trying to drill a side track well, and all this gas comes out. There was one specific case in South America when the whole you drilled into a cavern, and this whole mud, everything was sucked in, and the rig was sitting in the bottom of the lake. So, well control incidents happen, guys, and this is the reality of the oil field. Uh, we need to be very careful in our designs, right? Good engineering decisions on the rig side, and only then these incidents could be at least prevented from happening. So, what are impacts? Uh, Increased exposure to hazards, NPT costs. You know all this. I'm not going to waste time here. I'm told I have 1.5 hours only, and 45 minutes is gone already. So, impact of a blowout, long term, company images at risk, remediation, environmental pollution, reservoir damage. You are depressurized the reservoir, whatever. deferment, reduction, loss of blah blah. All right, let's come to field examples, guys, and we are going to review 4 well incidents where we took the cake, we were able to manage the cake in 2 cases. We are talking about actually 6 wells here, but then I will discuss only 4 of them. And you see, in some wells, the incident took a long, long time before the primary control was restored, right? So in 2 wells, well B and well A, it took almost 22 and 28 days. Whereas in other wells, the um, well control was achieved in 1 and 2 days. So different kinds of situations, right? Look at this graph. It says influx taken before the well was shut. So there are situations when 100 barrels of influx was taken, 10, 13, 3, depending on how fast we have reacted to the influx situation. What does that mean? And that means the ability to identify an influx situation is very important from the perspective of well control in our um, real time operations on the rig side. Ability to identify. So on one well, you had 100 barrels taken over a couple of time, and of course, the porosity and permeability of the reservoir is equally important to flow. Whereas on the others, you had just 3 barrels and you were able to shut in like this. So you need to have very agile minds. You need to have uh, people on the rig who are able to take quick decisions, understand the well, talk to the well, and make the right decisions at the right time. And then let's go to the well and let's go to the different situations we run into. So this is a well A. I just named it. So the operator is not identified. But let's see. Here is a well, 2167 meter TD, and we were drilling in MPD mode. For those of you who don't understand MPD, it's managed pressure drilling. It's just one way to have a better control over the bottom hole pressure. Now, when talking about a kit, the main purpose is to have a good control on the bottom hole pressure, right? So this tool really helps us. So just like you will have a pump on the rig, the MPD also has its own pump, and um, it puts an additional pressure on the well, and by that it kind of minutely controls the pressure on the bottom hole. Uh, so we were drilling 12 and a quarter inch hole. We had 11 ppg synthetic mud at the depth of 2151 meters. Now you observe the circulating background gas increase from zero point 0.1 to 1.8. Yeah. Now, guys, what does that mean? If you are observing an increase in background gas, is it really a confirmed uh, sign of taking a kick? No. We know that this means that the bottom hood pressure is increasing, right? Zero point 0.1 to 1.8, well, you definitely need to start observing the well. And as well, that's the first reaction on the well of the drilling supervisor. It's, oh, okay, there's more gas. Let's increase the mud rate from from 11 ppg to 11.7 ppg. Well, was it a good decision? We'll find out. Yeah. Then it says continue drilling to 2167 MDDF with 100 psi back pressure ECD 12.4 and observed an increase in return in flow. So what happened here, guys? Observed increase in return flow. Is it a sign, a confirmed sign of taking a kick? Yes, it is. Remember my slide on confirmed signs of taking a kick. Observed increase in return flow. So when you took this kick, yeah, you know that there's something wrong. You should have immediately shut in. And there was one more point, guys. When you have background gas increase, should you just go ahead and drill, or would you just stop first and do a flow check? Think about it, guys, because the guys in the rig are under tremendous pressure all the time. What I would like you as engineers and operators on the rig side, whether now or in the future, to identify this. Okay, what if I come across a situation where the gas is increasing? The first thing it says is flow check. That's the only tool we have on the rig to identify are we in a situation. All right, they observed increase in return flow, shut-in well on annular, and then shut-in drill pipe pressure, 300 psi, drop to 100 psi, shut-in casing pressure, 600 psi, and drop to 300 psi. All right, decided to kill well using driller's method. So they decided to control it by two circulation. Okay, so what is our observation? Increase in connection and background gas was observed. The well was not flow checked. Didn't I tell you the first thing you should do is flow check the well? Leads to not following on warning sign. So who didn't follow the warning sign? The guys on the rig didn't follow the warning sign. And they are all IWCF qualified, right? So despite having all the qualification, they were not really looking at the connection and bottom background gas. And okay, it's okay. We will just drill a little more and we'll case off. Hey, that doesn't happen. You have a warning sign, stop right there and flow check. All right. So here it says, well shut in while pump was still running at 158 GP. What does that mean? You have closed your ramps, right? Or your annular. So nothing can really go out in big hole. Now everything is going through the choke. And here you're pumping in at 158 gallons per minute. What is going to happen? And then it is saying MPD back pressure was 180 psi and increased to 300 psi moments before the well was shut in. So we're talking about an increase in managed pressure drilling back pressure, MPD back pressure, yeah, and also the pumps are running. So first of all, if you keep running, if you increase the back pressure from MPD, you will see an increase in flow, yeah, because what goes in comes out on the other end, right? And you keep your pumps on. What will happen? If you keep going on, it will reach where you're going to fracture the formation. And you fracture it, then an influx will begin. What does that mean? You're causing trouble to yourself. Why do you have to keep your pumps on? Resulted in formation breaking down at initial shut in. Look at it, guys. Yeah, MPD pressure not maintained during connection prior to kick. It was not maintained. You increase from 180 to 300 psi. Any specialist on managed pressure drilling will tell you that you should maintain the back pressure constant if you are in a connection mode or you drilling mode. You don't want to change. the back pressure. No mention of increase in flow back at this time. So if you increase the back pressure, there should have been an increase in the flow back. What does that mean? If there is no mention of increase in flow back, that means you are losing the fluid somewhere, right? And when you're losing, that means you're losing into the formation. The sharp decrease in ECD can be seen. Yeah, you can see it on the graph. And probably influx was taken in this time. See, this is how we mess up on the rigs. Manage pressure drilling. If you're using that, you must know the basic principles of how you run the show for MPD systems. All right. How was it handled? There was another thing we observed. We pumped 34 barrels, 11.7 ppg at 30 SP. No response on shutting. So what he did, he increased the joules. He said, okay, not 30 SPM, let's do it with 35 SPM. God damn, don't you know that in a driller's method, during first circulation, you're not supposed to change your SPM. That, that rate shouldn't be changed. But they changed the pump rate, yeah? So if you change the kill rate and you hope that the kick has been circulated up, I'm sorry, that's not going to happen. So guys, then they say beginning of second circulation, while pumping kill mud rate down the drill pipe pressure should drop. Yes, beginning of second circulation, you are having a kill mud, and what did we say? We said that the as the kill mud goes down and the final circulation pressure is not showed, and there is a steep fall in the pressure between ICP and FCP. However, what did they do? They held the pressure constant at 330 psi. What does that mean? Man, you have already gradually increased the bottom hole pressure to the limit, and the formation is fractured, unfortunately. And everything was happening over a period of time, and there was nobody to identify this. What does that mean? That means we did not have competent people on the rig, right? All right. So here are the root causes identified. The people on the rig lack awareness and understanding. They didn't act on the warning sign. They failed to adhere to MPD procedures. The well was shut in with pumps still running at 300 psi, which means MPD process was not followed, which led to the formation of backtracking initially, the initial shut-in. There was a slow response, almost took 11 minutes to shut in the well, and the well control procedures. Now we will discuss 3 to 4 wells today, and you will see that the root causes, the conclusions, the lessons learned are very similar on the wells where we took the kit. And there have been studies on various kits globally by different well control companies. Very similar results have been observed. So we often blame Mother Nature, but as engineers and operations personnel on the rig side, there's a lot we can do to make our working environment safe. And that's why this presentation is important. Okay, well B. Drilling 8.5-inch hole at 3340 meters in LPD mode. Mud weight 17.1, back pressure EMW with MPD 81 while making a connection. Okay, observe increase in flow out and active peak. So, well, increase in flow out and active peak. Guys, just throwing around this thing at this time. Could this be a ballooning event? Now, for my college students, just I will explain what ballooning is. Uh, Ballooning is nothing but an formation takes in some information in the mud, and when you shut the pumps off, it gives you back the mud. So initially you think that you're losing mud, and you just like in a kick, and just like in a lost circulation situation scenario, you're losing mud. But when you switch off the pump, this um, mud is coming back in the hole, and that action, that the mud which comes back is a situation you think that this is a kick. So given that you are making a connection and you observe an increase in flow increase. Now flow increase is a definite indication that you are taking a kick. But the rig guys considered it as ballooning event. But why should you take it as a ballooning event? They thought that the well is flowing back with the pumps off. Yeah, that's how they can think of uh, it as a ballooning event. But I will show you that how camouflaging a ballooning event can be, because here it's a matter of pumps on and off, and between pumps on and off there is not a significant pressure difference of 400 psi. We'll talk about it later on. Huh? What mud pumps online? So, and remove the MPD pressure, MPD crew, hand it over well to driller, shut in on DOP, observe return flow and active increase, continuous increase, all right. And then you quickly shut in the well on annular and observe drill pipe pressure of 220 psi and shut in casing pressure of 650 psi. You see the difference? 400 psi difference almost, 430 psi. Uh, Could pumps on and off lead to 430 psi? I would be down. Anyway, let's go ahead. So they use driller's method on this, and what we see here is we observe that warning signs were not followed, drilling breaks during the day, 2 hours before the kick. 2 hours before the kick even happened, um, there were drilling breaks, so the formation was changing, but nobody bothered to have a load check. There was a substantial increase in bottom background gas, but um, they, they, they didn't really bother to do a flow check. They changed the filter sign. Yeah, on an HPHP well, the practice is that you will not change the people on the bed during drilling. At least finish that section and then change people. They will change the filter sign. These are basic drilling procedures, manuals, processes, which are not being followed. Yeah. Now you see that pressure going down. Yeah, the pump pressure has been decreasing significantly, and and that over a period of time, 2 3 hours maybe, they have been drilling all this time, and that trend was not picked up nor investigated. So uh, we are saying lower density mud going in the hole. Now, just before that, we said that there was a drilling break. If there is drilling break, obviously the gas is going to increase. That means you're going to have a mud cut uh, uh, gas cut mud, and going in the hole, which will reduce the bottom hole pressure. So none of that was identified. You see how failures happen. It's not just one reason for the kick. There are so many things here which were not identified. Then how was the incident handled? Well, it was killed using driller's method, initial circulating pressure. Yeah, the uh, flow rate circulating pressure, they had that number, and then that is 630 psi. But it was observed that the initial circulating pressure was way below the ICP, even to start with. So you are below ICP, and that in itself is a big problem. Why? Because that's a requirement for a driller's method. You must be at ICP to start with. Then you see they had different flow rates, 148 GPM versus 163, corresponding to different strokes per minute. Yeah, 30 and 32. So they were changing the flow rate all the time. Now you don't play with that. So here you see valve breathing of ballooning was suspected. Oh gosh, yeah, big scientists on the rig, guys. Gradual loss while pumping. Flowback should have reduced with time, but here it was increasing. Flowback was increasing. Didn't we say that in the very beginning? And throughout the process, we saw that flowback was increasing. If flowback is increasing, why should somebody think of it as ballooning? And then you see 430 psi difference in shut-in drill pipe pressure and shut-in casing pressure, and you're thinking it's a ballooning effect. So what's the root cause? Lack of awareness and understanding. Not understanding difference between kick and ballooning. So even though you may have IWCF certificate, doesn't mean you understand difference between kick and ballooning. Not applying proven well-controlled principles while killing. Drill pipe pressure not held constant during first cycle of driller's method. ICP incorrect. 50 psi less than what it should have been, resulting in more influx during first cycle of driller's method. Not acting on warning sign. This is the first thing. The very first thing you need to say is if you're saying you have a drilling break, if you're saying gas levels go up, you're saying decrease in pump pressure, the first thing is stop. Stop where you are, pull up, pull down, make sure that your bit is in the right place and flow check. Yeah. Changing pit assignments. Don't change people during drilling the hole. Finish that section and then the first hole. Okay, next well. 12 and a quarter being hole being drilled with 10.5 mud weight with back pressure of 600 psi EMW 11.9. DFC performed every half stand. Yeah, dynamic flow checks were being done. Plan was to progress to the top of the basement and set your case. Attempted DFC but aborted due to gas in mud returns. Gas in mud returns. So there are two things, guys. One, they were not able to do a flow check. Oh, I can't do a flow check because there is gas in the mud return. So Coriolis meter is messed up. All right. But that's one thing we always said. What does a flow check identify? It identifies if you are getting close to an unwanted flow, uncontrolled flow. 2841 meters, observed increase in return flow. Flow check. Spaced out string and shut-in well on upper pipe valves. Yeah. Shut-in drill pipe pressure 1250 and casing pressure 13. Gain 13 valves. Driller's method to kill. Well kicked while drilling, increase in returns was seen by the driller. Okay, so he has seen a confirmation of increase in returns when he was drilling. So he has a confirmation already. So he shuts on the pipe ramp. First cycle of driller's method, the well was shut in on annulus. What the hell? Why do you want to change it to annular? You did the, if you really wanted to do it right, you should have shut it on annular to start with. Well should have initially been shut in on annular and filled on pipe. Casing pressure profile cannot be seen in the chart. Okay, so we didn't add some basic information in the text. Second cycle of driller's method can only be done if drill pipe pressure and casing pressure are same after the first cycle. So they had a difference uh, between the drill pipe pressure and casing pressure. Now this is not following the very basic knowledge as far as driller's method is concerned. If you circulated out the kit, how can you not have the same pressure? Improper procedure, flow check on positive indication of, guess what? What are people doing on the rig? They are doing a flow check after getting a positive indication of kick. So what is it that you need to know as drilling engineer? The first thing you need to know is to know what are the positive indicators of a kick. Yeah. Next, failure to act on kick warning sign. This is where you must do a flow check. Drilling ahead with high mud gas returns. They must have kicked. Well shut in on pipe ramps, then change to annular after first cycle of driller's method. Underlying causes, lack of understanding on conducting flow check, become MPD. Driller's method, second cycle applies, whereas weight and weight method should have been used. Why? 300 psi back pressure while killing prevented. Another kick. Real-time pore pressure not communicated to the ring. Improper procedure. Static flow checks not done, preventing accurate pore pressure prediction. Yeah, so you cannot predict pore pressure. This is a big challenge on the rig. You know, when you're operating, you're drilling, you really need to know what's the pore pressure. But the best way you can do is you can look at the sensors which are on the rig and identify, maybe look at the exponent, look at some kind of trending lines and identify there's an increase in perforation. So that should be done, and then you do static flow checks when you have MPD on the rig. So, okay, one more well. So this is the well, and we are drilling 8.5 inch hole. Uh, drill 29 meter in good cement. So they are drilling out of hole with 11.3 ppg mud, displaced to 9 ppg reservoir drilling fluid, uh, and drilling top plugs. Drilled out remaining shoe crack with 9 ppg. Okay, uh, now you look at this. Drill 29 meter good cement shoe with 11.3 and displaced to 9 ppg. Why? They thought that this is a good reservoir rock, and we have already drilled through it, and we know the pressure in this rock is 9 ppg. So let's displace the mud in the hole from 11.3 to 9 ppg. And then what happens? Observe increase in return flow and active system. So from 9 ppg mud, you can't expect to hold a pressure of 11.3, which means this was uh, drilling in virgin formation. Even though it was a proven field for a product producing field, the formation was virgin and it had 11 pressure uh, below the hole. And so shut in well with shut in drill pipe pressure 480 psi, casing pressure 925, 18 barrels, blah, blah, blah. Virgin reservoir pore pressure, which was never mentioned in drilling program. Right? So we failed to identify a virgin reservoir pressure. Um, it happens, but we could have been careful drilling on. But anyway, let's see what they did. They just before the kick, ECB showing decreasing trends. Okay, so mud density out is below 9 ppb at times, even lower than 9 ppb. Yeah? So 3 is pit level and return flow started to increase 10 minutes. 10 minutes before drilling this well. Okay, casing pressure profile and mud density is not available. All right, well killed by timely action not taken. Why? Why was timely action not taken? Well, because when the ECD was showing decreasing trend, yeah, ECD is decreasing trend. That means you're losing pressure somewhere. How would you lose pressure in the bottom hole? That means there is some kind of influx coming in, and maybe there is some salt water there. There's something there which is reducing your bottom hole pressure, and then pit level and return flow started to increase. So again, this is a confirm, and we have not really shut in the well until when we shut in the well uh, when we saw a return flow in that system, whereas ECD showing trend decreasing trend already. Yeah, in and out differences were there. All right. Timely action not taken, pit level increase and return flow increase started 10 minutes before the well was shut. ECD was showing a decreasing trend. Underlying causes, displacement to 90 degree mud was not done in controlled manner. Only one barrier. Only one barrier. What was that barrier? The cement below in the stream. That was it. Kick in this well was handled in the best manner. Amongst all the 4 wells we have seen, the kick here was handled in the best manner. Casing pressure profile and mud density profile not available. So this is a common thing. What you gonna do? You think I have calculated kill mud weight, and for that I just need the verify pressure, and this is enough? No, you need to know that what's happening on the casing side. Why? Because the kick is on that side. You need to identify the kick volume. And to identify kick volume, you need to know what is the pressure on the casing side. Mud density in profile is not available. So this kind of shit happens. Now let's conclude from what we have learned, what we have seen in 4 wells, and also based on your basic kick and well control situation analysis. We can see that accurate pore pressure prediction can help reduce well control. That's one big thing we wanted, but we know that it is very much sort of an impossible thing to do to predict pore pressure ahead for 500 meters below the bed. But we try to do it by VSP, by different methods, resistivity. At least we can try to find some trends. And the more time we spend on this kind of analysis, the better we, the better prepared we are developing incidents. So 4 out of 7 wells kick in the RAM, carbonated pressure RAM. So what is a RAM? Where the pressure changes significantly in a very short uh, distance, as we build it. Accounting for fracture gradient in shale, sand, and coals. That kind of accounting was never made in drilling programs. What does that mean? Shale would have is an impact on the fracture gradient. Sand and coals, likewise. So when you take a shale, you are on the high side. A coal will just crack and you can lose mud and loss circulation will happen very quickly. So that was not taken into consideration many times. Mud compressibility. Why is mud compressibility important? Because the gas cut situation is very common. And when you drill with the synthetic mud, the gas tends to dissolve in the mud, and then you don't see the gas in the near future. I mean, until this thing comes up above, you know, very shallow, and all of a sudden that thing comes out of the mud. To include kick intensity in planning apart from the organs concerned. This was one of the things we had because the kicks were happening in the ram. The concept of kick intensity seems to be very important, and you can identify intensity changes in the ram more closely than kick organs concerned. So that was one of the recommendations we had. Then we have swap kick versus kick intensity for exploration wells with pressure ramps. Yes, swap kick versus kick intensity. There are times when you kind of induce the kick, and you can do different analysis studies, put together charts, and identify a swap kick. This is, kick in a ramp, pressure ramp. You definitely need to spend time identifying gas solubility for well control incidents. Now, the mud companies are getting clever, they're much clever now than they were 10 years ago, and they can pretty much identify gas solubility, the extent of solubility, gas gets soluble when you're dealing with synthetic mud that can be identified. Narrow pore pressure fracturing challenge is a challenge in deep water wells due to the overburden pressure, reduced overburden pressure, and small margins between pore pressure and fracture pressure. So there, that really impacts well control incidents. If you're not able to play with the bottom pressure, then you may end up cracking the formation or not tracking, maybe taking an influx. In both sides, it's a big problem, and we have seen that there were incidents of loss circulation followed by increase, put some kind of material there, increase the mud rate, circulate around, try to control that loss, and then you end up cracking the formation somehow. You take an influx, and then the level of mud in the hole goes down, and then the influx gets even more, and then the situation becomes uncontrollable. Hydrates are one thing which can cause problems, well controlled, and specifically in natural environment. Um, and there are good amount of fluids available to take care of hydrates now, but not you come back. Now, fingerprinting is another thing which is very important, very useful when identify a kick versus a balloon in safe example. And that should be used more and more. That said, finally, the concept of bridging document, because if you have drilled part of the well on a particular rig and then you bring in another rig to do completion on that, or maybe you change the rig for whatever reason. Um, the the a new bridging document for the well should be put together because each rig has its own each rig, each operator, company, and noble versus transition. There may be procedures that should be different, and how you handle kicks, how you handle loss circulation, all those things may be different. So these were some of the challenges when it comes to kicks and well control management. And the recommendations we made, you can say the lessons we learned here. Key recommendation for both entity information wells were, critical key person well involved in well control and killing have to be properly trained. What is properly trained? Of course, you can have IWC, but that's not enough. They need to simulate situations in the so you need to have uh, well controlled equipment on the in the operator's place, and we should be able to simulate different situations. So very much similar to IWCF, but more drilling oriented, more operations oriented, actual situations which we see when we drill the wells. An operator may have a specific well, and he may have all the data around that well where he took a kick, and that data should be put into the simulator, and people trained on that simulator. So actual well-related training was recommended. Like I say, IWC training is not sufficient. Advanced well control or team-based well control courses involve practical and troubleshooting. So team-based is very important. A person may not learn a whole lot just with doing things by himself, but you make a team, a driller, you have a driller, you have a people, you have all the people you have on a drilling rig, and you try to do a simulating exercise with all of them, literally not under pressure that you will fail or you will pass an exam, but just if you can identify what is right or wrong, and that can really help you. Well-controlled competency of the office and rig team to be assessed, gaps identified, and flagged. So where are the people who can do this kind of competence assessment? Of course, when you send somebody IWCF, an IWCF, they will be assessed. But we have people in companies, many big companies like BP and Shell do have um, but how often, uh, you know, how often are those people brought in for operations monitoring or supervision? So that should be the goal for operations. Teamwork in terms of monitoring and detecting and shutting among so good teamwork is always a good thing, guys. And I would recommend that this should, these points should be made applicable to operators for all the young engineers to go for IWCF exam. They should learn from this and identify the issues. So this is pretty much what I have for you guys. And if you have questions, I think
Thank
I'm
you so
open
much.
for, yeah, go ahead. Go ahead.
Yes, sir. Yes. So first question from Saurabh Ranade. So, sir, in case of loss circulation, what other option do we have to prevent a kick blowout besides plugging the zone of loss by cementing or adding loss circulation materials or visco fires to lift more suspended drilling cuttings?
Right. So um, major solution is like what he say. You add specifiers. You try to plug in some. But the other thing, the first thing which operator on the rig uh, really should do is try to reduce the mud rate in such a way that, of course, shouldn't take an influx, but on the same time, it has too much of
Okay,
yeah.
okay, sir. Just participant, if you have any question, you can just post on the chat box, or you can
Very
raise your
good.
hand.
Yeah.
Anyone. I think no more questions, sir. So
Very good.
I think
Very good. I think
okay, sir.
it was a good session. Yeah.
So yes, sir, it's a
Guys,
really great session, sir.
please do give your feedback to PEA, and I will appreciate to have the feedback. And many thanks to PEA to have put together this free presentation for all of you. I appreciate your time and thank you very
Thank
much.
you so much, sir, for this wonderful session. I, behalf from the Petroleum Engineers Association, thanking Dr. Nitesh Kumar, sir, for this valuable presentation and for his valuable time. I like my all dear participant to kindly fill this form, feedback form, and give your valuable feedback. So thank you so much, sir, again. Thank you so much, sir, and thank you so much, participant. Hoping to see you soon in our upcoming events.
Okay, dear.
Thank you
Thank you
so
very
much.
much. Okay,
Thank you
bye.
so much, sir. Have a good day ahead, sir. Guys, kindly fill this form for the certificate purpose, and you will receive your certificate within 7 working days. And kindly like, comment, and share your feedback on our LinkedIn official page. I have saved the link on the chat box. So again, thank you so much, sir.
All right. Thank you.
Thank you so much,
Bye bye.
participant. We are closing the meeting.
Good.